All right, so we're gonna watch our second video on PES here. I'm gonna do the same thing. I'm gonna stop it and talk to you about it. This is another MIT video. I think this one's a little bit higher level than the first one. That's why I like to show that first one first, because it starts at sort of a level of zero knowledge. So first, I'm going to show you this is MIT, right? One of the top universities in the world. And I want to show you the professor right at the beginning for the first couple of minutes, just because I think it's funny. And then we're going to skip ahead to where he talks about PES. You can see he's talking about periodic table test, off-ball principle, de Broglie, Heisenberg, Schrodinger. So some of the same things we've talked about in class. Let me sort of show you the first couple minutes here.
5 p.m. You get the submissions to me either over the internet, or if you have something majestic, you have to cart it in with the riggers, get it to my office. Last day we had the lesson on the Aufbau principle, and the Aufbau principle gave us there's still too much talking. Still too much talking. I will tolerate zero talking. When you walk through that door, I'm assuming it's an act of free will. And when you walk through that door, we enter into a contract. The contract goes something like this. You have certain expectations of me. You expect me to come to class prepared. You expect me to treat you with respect, not to use vulgar language, not to say things that are insulting, insensitive. And I have certain expectations of you. I expect you to come to class prepared. I expect that you've done the reading, and I expect that you're going to sit quietly, absolutely quietly, because it's my duty to preserve a fertile learning environment. If you don't want to learn, I don't care. I don't care. But if you impair the ability of your neighbor to learn, I will take action. It's very simple. Very simple.
I love that. I just think it's funny. Top university in the world, and here he is having to tell them several times to be quiet. So we're gonna skip ahead here to where he actually starts talking about photoelectron spectroscopy. Some of these same things you're gonna see. He's talking about ionization energy here, and so we are looking at here's hydrogen, helium. So he's outlining 1s2s2p. Again, some of the same things that we talk about in class. And so I'm going to let it roll for a little bit, and then I'll stop it and explain to you what's going on.
There's a little jog here at oxygen, because here we've got the 3 unpaired electrons for nitrogen, and then there's the oxygen starts to pair, and we continue to neon, and so on. 3s, 3p, 4s. So you can see the relationship between that property and its the place of the element in the periodic table. So how do we measure these values? Well, I thought it might be a good opportunity to revisit the whole question of gas dynamics, and also understand the measurement of ionization energies. And the technique that's used is called photoelectron spectroscopy. Photoelectron spectroscopy. All right, and it's got a 3-letter initialization, PES. All right, so I want to show you a cartoon of how this works. Actually, I took one, and this is taken from the text we used to use. I like the text that we're using now better, but there are a few things in the other text that were good. So we've scanned these few pages and posted them at the website if you want to go through and read this stuff. So let's jump over to that. So here's an example of a terrible drawing.
This should look really familiar. So you can see we have that same idea of the atom beam coming in through here, right? And then we have the same idea of the photons. We were, the last video, talking about just X-ray photons coming in. Today, this video, we're going to throw in ultraviolet UV photons as well. And then again, that's going to kick off the electrons, right? And then depending upon how fast they're moving, that determines how much they bend in this magnetic field or electric field. It could be either one. And then from that, we have this detector that picks up where they exist, right? So we're going to talk a little bit about this. He's going to...
I look at this and I haven't got the faintest idea how this thing works. it's not the artist's fault. Somebody should have proofread this thing. What they should be doing is showing something like this. So let's see what's going on.
So here's his point, and he's going to get this to you. The atom beam, he's saying that should be called the specimen atom beam. And he's saying that we're not really shooting this atom beam like we said in the last video. We just sort of place it here, okay? And then because we need to be able to direct these photons and hit that specimen, if this were truly a beam of atoms, that would be really, really difficult because, as you know, atoms are incredibly small, which we could have them spread out, but then it's not going to be nearly as effective. So, and then the electrons that are kicked off there, he's saying that those are the photoelectrons. The energy incident. So in physics, you learned, probably not, but in light, you learn about an incident ray. And that's the light that strikes whatever you're talking about. And so in this case, the energy of the incident would be the energy of the X-ray photon or the UV photon. That is incident on the specimen. And then over here, this is the energy of the photoelectron, which again, the photoelectron is just the electron that's being kicked out. Okay, so he's going to explain all that.
All right, and it's got a 3-letter initialization, PES. All right, so I want to show you a cartoon of how this works. Actually, I took one, and this is taken from the text we used to use. I like the text that we're using now better, but there are a few things in the other text that were good. So we've scanned these few pages and posted them at the website if you want to go through and read this stuff. So let's jump over to that. So here's an example of a terrible drawing. I look at this and I haven't got the faintest idea how this thing works. It's not the artist's fault. Somebody should have proofread this thing. What they should be doing is showing something like this. So let's see what's going on. So what we're going to do is we're going to bombard a specimen right here, which they never show. I suppose this atom beam is supposed to be colliding with the photons. That would be quite an apparatus to build, let me tell you. But instead, what you have is you have the apparatus sitting so that you've got the material in the center of the chamber, and you irradiate with photons. And the photons have very, very high energy, and they dislodge electrons. When they dislodge electrons, that's the ionization event. And then what we do is we measure the velocity of those ejected electrons. And if we know the velocity, we know their energy, we know the energy of the incident energy, and by difference, we calculate the binding energy of the electron in the atom. So let's take a look. I'm going to draw a cartoon here that gives you a sense of what's going on. So here's the n equals 1 shell, or the K shell, and then I'm going to show, say, a second shell here. 1, 2, 3. So this is the L shell, or n equals 2, and you might say, gee, he's got that wrong. It's kind of simple and so on. It's as complex as it needs to be for the explanation. Don't let accuracy trump clarity. The real accurate picture here is too detailed to convey what I'm trying to convey. So this is the specimen, all right? Let's call this the specimen.
So that would be whatever atom we're looking at. So this would be, in this case, 1s2, 2s2, 2p1, which I believe is boron, right? Yeah.
And I'm going to irradiate the specimen with some radiation of high energy. And so I generally indicate the photon by a squiggly line with an arrow.
Now, in the last video, that photon, we just talked about the X-ray. So that's what he's drawing there. That's the X-ray coming in, which we call the energy incident. And it's going to hit that electron, okay?
To indicate it's got wave-like properties, and I'll usually write h nu next to it to indicate that it's a photon of energy h nu. So the photon comes in, and if the energy is high enough, it will dislodge an electron. So this electron is dislodged. It's now ballistic. It's rendered ballistic. It's free. It's ionized. Okay? It's gone. It's gone. And what we're going to do is we're going to take an energy balance here. Now, at some point, you may come back and learn some quantum mechanics. This photon is annihilated at this collision. So the photon doesn't act the way an incident electron does, where it loses some of its energy. All of the energy is lost. So this photon's gone. All of the energy is given to this electron. So let's do an energy balance here. So I can say that the energy of the incident photon,
So in the last energy balance that we looked at in the video, that would be the energy of the X-ray.
Is now going to be given to the electron. It's now got some kind of kinetic energy, right? E kinetic.
Same as last time.
Plus the energy it took to pull it out of the atom. Plus E, let's call it binding. E binding.
So again, that binding energy is the energy that's required to remove that electron because of the force of attraction between the protons and that electron.
Okay? And we know the incident energy of the photon because we're running the experiment. So we set the value of the incident energy of the photon beam, and then we send this to a detector. This goes to a detector. And the detector measures the velocity and ultimately gives us the energy of the scattered electron. This is called the dislodged electron or photoelectron. It's the electron that was kicked out by the photon, so it's known as the photoelectron. Photoelectron, pardon me. Let's try that again. Photoelectron energy is measured at the detector. And then by difference, we get the binding energy. So this is h nu. This one here is going to be a half mv squared. And then by difference,
So 1/2 mv squared kinetic energy, right? So that's what he's saying there.
we get the binding energy. And what kind of photon energies do we need? We need fairly high energies. And so typically, we might use wavelengths down around 1 angstrom, which then makes it an X-ray. And so over here in building 13, we have such instrumentation, and the material scientists would call this XPS.
An angstrom is a unit of measurement. So it's like a nanometer, but it's not. It's an angstrom.
X-ray photoelectron spectroscopy. And if you don't want to blast all of the electrons out of the specimen and just get the most weakly bound, then you want a lower incident photon energy, which means a longer wavelength. You might come in at around 100 angstroms, which is ultraviolet. You know, people, the general public is so afraid. They don't know science. If they say X-ray, if they hear X-ray, they get all panicked, you know, it's radiation, their children are going to die, and all this kind of stuff. So what people will do is they'll say, instead of soft X-ray, they'll say hard ultraviolet. And then the public thinks, oh, as long as I wear sunscreen, I'm going to be okay. So that's so if you use hard ultraviolet, it's called UPS. It's nothing to do with brown trucks. It's ultraviolet photoelectron spectroscopy, and collectively this is known as PES.
Honestly, that's probably a little more information what you need to know as far as the XPS and the UPS, but it's important to recognize that we can use different amounts of energy.
Photoelectron spectroscopy. All right, so now let's go back to this schematic. Now you can see how bad this schematic was, that these photons are coming in as so and striking the specimen here, ejecting the photoelectrons, which then are focused and ultimately measured here at the detector. So there's the energy balance. The energy of the incident photon is distributed across the kinetic energy of the photoelectron plus the binding energy, and this is how we measure all of these quantities. So since you're using very, very high intensity radiation, there's nothing saying that you're going to eject only one electron. You can eject a plurality of electrons. And the different electrons have different binding energies. So you're going to get a set of binding energies, which means you'll get a set of lines. You'll get a spectrum of energies. So this is what the spectrum looks like. And this is, by the way, just a general way of looking at any spectrum so that you train your eye to know what to look for. If I look at any spectrum, I'm going to have a plot of some kind of intensity unit versus some kind of energy unit
So important to note, when we talked about mass spec, look at what we had. We had intensity versus energy. In this case with PES, again, we're looking at intensity versus energy. So that's going to be a spectrum that we see.
And sometimes energy increases from left to right, but sometimes they might put energy increasing from right to left, as you see in these spectra. But energy is along here. And intensity is related to population. All other things being equal, if I have a specimen that has 2 times the concentration of active species, I'm going to get twice the strength of the line. So the intensity measures population. The energy is related to the characteristic binding energy of a particular electron, so the energy is related to the identity of the species. This is how we can identify certain species.
Again, tie that back to mass spec. How did we identify the isotope? In that case, we identified the isotope based on the mass that was along that x-axis, right?
Already shown you, if you walk in and you see those 4 Balmer series lines on a spectrum, you know that's characteristic of atomic hydrogen, nothing else. So those are energies. And then away we go. So we have a line here, but we know that real data have a little bit of a spread to them. So you don't see discrete lines, you'll see a spread centered at about the value. Okay? So let's look at these. These are highly stylized, but here you can see, here's boron, for example. So these are the 1s electrons of boron. And
okay, so let me just real quick. What you're looking at here is 4 different elements. We've got boron right here. Here's beryllium. Here's lithium. Here's helium. And here's hydrogen. So these are 4 different PES all plotted on the same graph. Okay, the up and down portion of it doesn't have any effect. Think of it as this is the new x-axis, this is the new x-axis, this is the new x-axis, this is the new x-axis. Okay.
They're held at a binding energy of about 19.3 megajoules per mole, and then this is 2s, and here's 2p. Now there's a difference between 2s and 2p, but they're of the same order. They're roughly about a megajoule per mole. There's subtle differences, right? And this goes back to Sommerfeld, who said that even though there are s and p orbitals, there's a circular orbit and there's an elliptical orbit, but they're roughly in the same shell, and that's what you see. But there's a huge difference in going from shell n equals 1 to n equals 2. This is not to scale. You see they got a little break there. All right? And now look, what's the electronic structure of boron? 1s2, 2s2, 2p1. There are 2 2s electrons, but only 1 2p electron, and this is trying to show that the height here is twice the height of the 2s peak. So you see that we've got 2 of electrons here, 1 electron here, and it's easiest to pull out the 2p electrons first. All right? And you go on, there's beryllium, and so on. So we see that we can build data in this fashion here. We keep going. Here's carbon, which is 2, 2, 2, right? And then oxygen has 2s2, 1s2, 2s2, 2p4. So this is 2 electrons, this is 4 electrons. It's showing that the 2p height is twice the 2s height. And then finally neon is 2s2, 2p6. So this is roughly 3 times the height of the 2p.
There you go. So that's PES. And you get pretty much the idea of it. There's one more video you're going to watch. I'm not going to narrate that one because that one's at probably the high school level, and so that's a little bit easier for you. So after you're done watching this, come on back to the Zoom, and we can discuss all these ideas that you have going about your noggin.